Welcome to Texas State University's Chem 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin. We will continue with Chapter 5, Part 5, Reactions of Alkenes and Alkynes. Okay, so in the last video, we learned about carbocations were a major contributor to the selectivity of these reactions and the Markovnikov's addition, as well as the formation of a dihalo species. Okay. So now that we know that carbocations exist and we know that they have a relative part of stability, one thing that they can do is rearrange to form the more stable carbocation. Okay, so we need to think about these carbocation rearrangements as a possibility when we do this. Okay, so the product of these electrophilic additions to alkenes typically involves the breaking that pi bond to form two new sigma bonds in its place, okay? And in the following addition, only 17% of the expected product is formed. So what we think is happening is there must be some reason for it to move around such that we get the actual product we see. So let's look at this reaction and see why it might be rearranging, okay? So in this product right here, we have a formation, and using Markovnikov's rule, we would expect that the hydrogen to end up on here and our chloride to end up here. And so this is our predicted major product from the reaction, because we can't form the primary carbocation here, and this would form a secondary carbocation here. So between the primary carbocation and the secondary carbocation, this should be our major product. But unfortunately, only a little bit of it forms that. The major product is actually a rearranged compound where one of these methyl groups has transferred over one carbon. Okay, so see how we had to move a methyl group to get to this major product here? Going from over here. So instead of being a methyl group where this chlorine is now, that methyl group has been transferred to the next carbon over. There must be a reason for this kind of rearrangement, this moving of this methyl group here. And it all has to do with carbocation stability, okay? So in this rearrangement, we either have an alkyl group or a hydrogen group can migrate one bond, one carbon over, and only one carbon over, to give us a more stable carbocation. We call these rearrangements a 1-2 shift, meaning they can switch from one carbon to the next carbon over to give a more stable carbocation. So let's look at that in a little more detail here. Okay, so as with all of our mechanisms, the first thing we're going to do is we're going to start with that proton, addition of the proton to give us our first carbocation. Okay, so when we do that first addition by Markovnikov's rule and by carbocation stability, we're going to end up with our carbocation on this second carbon here. Okay, so we're not going to move it over here because that would be a primary carbocation. Okay, now if we look at this intermediate here, right here, it's a secondary carbocation, and that's okay, but a tertiary carbocation would be more stable, okay? So we have an opportunity for taking the electrons that form this sigma bond, moving them over one bond to where the carbocation was. When it takes those electrons with it, it yields a tertiary carbocation, okay? So we started with a secondary carbocation, we moved one sigma bond over, either a methyl group or a hydrogen. It has to be something with very small mass, like a methyl group or a hydrogen, moving it over one carbon to yield a more stable carbocation. Okay. Once we yielded that more stable carbocation, now it reacts with the chloride ion here to give our final product here. Okay, so let's talk about why this is happening, okay? Okay. When we do this kind of rearrangement, again, we can move either a hydrogen or methyl group, and it can move over one carbon if and only you're going from a less stable carbocation to a more stable carbocation. Okay. We see those rearrangements also happen in acid-catalyzed hydration of alkenes. So it happens when we add water across that double bond, because what we'll do is we'll again transfer a proton or a methyl group over one carbon to yield a more substituted carbocation. That more substituted cation will then react with the remaining water in the reaction to give us our final product. Okay, so if that's true, if we can do these rearrangements, occasionally we'll see weird things happen, like rings will change size. Let's look at how we can do that mechanistically through this idea of a 1,2 methyl shift or a 1,2 hydride shift. So in the case of this compound right here, we're going to add our hydrogen to this bond here. So because that'll give us a secondary carbocation right here, okay? So now we have this as a secondary carbocation, and we have our hydrogen on the end of here, okay? We have a hydrogen here, that could move a hydrogen over here, or we have this actually can be a methyl group that can move over here. If that methyl group moves over to here, we have 1, 2, 3, 4, 5 carbons forming a ring. So that means we have this carbon here is that carbon there, and let me draw this methyl group here is now this methyl group there. So we've moved this methyl group over to this carbon, giving us a 5-membered ring. And then this group right here is still this methyl group on the end. And we formed our tertiary carbocation, which is then the bromine adds to it at the end, okay? So let's look at this last one and see if we can't figure out how this one's working now. I'm gonna use green now so we can do it. So let's see, if we're gonna add water across here, that means the hydrogen's gonna add to this side, giving us a carbocation here, okay? Ooh, that's a tertiary carbocation, okay? So, but what we also have is we have this carbon here has 4 carbons bonded to it. So what might be happening is we might be breaking this bond and moving it over here to give us this internal carbocation here that would also be tertiary, and it also opens a ring up, it relieves ring strain. So we go from a tertiary carbocation in a 5-membered ring to a tertiary carbocation in a 6-membered ring. So that might be the driving force for that. And once we form that carbocation on this right here, it'll wait around until water reacts with it to give us our primary alcohol. I'm sorry, our tertiary alcohol, our final product. Okay, so let's talk about some of the rules associated with this 1,2 hydride or 1,2 methyl shift, okay? The carbon bearing the positive charge is always sp3 hybridized, okay? That means it has 120-degree bond angles. And tertiary is always more stable than secondary, which is all more stable than primary. The carbocations are stabilized by the fact that the electron inductive effect is helping dump electrons into that positive charge to stabilize it. Methyl and primary carbocations are not stable because they do not have those things that they can pull electron density in. Carbocations can rearrange by a 1,2 shift if when they rearrange, they form a more stable carbocation, or in the case of rings, it makes a larger, less strained ring. The most common observed pattern is going from a secondary carbocation to a tertiary carbocation, or going from a small ring tertiary carbocation to a larger ring tertiary carbocation. Okay? Now that means that our carbocation intermediates can undergo 3 types of reactions. Okay? They can rearrange in a 1,2 hydride shift to make the more stable carbocation. They can have the addition of a nucleophile to form a new covalent bond, i.e. the halide ion or the water to make an alcohol. And then the loss of a proton to give an alkene, the reverse reaction, to give us back our system. Okay, So they can either move forward and give us our final product, or actually lose the proton and go back to the alkene, and we just have starting materials again.